Welcome back. I think last time I wasn't sure if I did associativity of addition. So let's see. The method is always when they have alpha, beta, and lambda to use the definition of a complex number that its form is a plus bi. You write that. So, and you just use, because alpha and beta are different, instead of A and B, we just use like C and D or E and F. And in associativity, you have to add them to get, I could put them each in parentheses, but you add them first in the parentheses and then you add, and you want to show that that is equal to adding in the other parentheses first. Alpha plus beta, then plus lambda is the same as adding beta and lambda and then doing alpha plus that. So using the definition of addition, the A and the C combine and the B and the D combine in the parentheses. Then using the definition of complex, you see, I used I didn't use, this is not right on the right-hand side here. I scribbled this down during my lunch at work or whatever. Probably, at least I think that's when I did this. This is in the form of a complex number, and this is in the form of a complex number. So you add the real and the imaginary parts. Now, because real numbers are associative, you can do the C plus C first. And because the real numbers are associative, you can add the D plus F first. So I don't know what this stuff is here. So, and of course, you could move the A, C, and E, and B, D, and F around if you want because of commutativity. Anyway, because of commutativity of complex numbers, you can do A plus BI. So we proved commutativity earlier on in the chapter. So we can use that here. The A and the BI being added here. And so the C plus E and the DF are added here. So you have A plus BI. And over here, you have the C plus E and the D plus F are two complex numbers that were already added first. What complex numbers were already added first? Well, the real part, this is C plus DI and E plus FI. The definition of complex addition makes this equal to this. And so you have the second parentheses. So that's pretty much the argument. The stuff on the side, some of that might not be right, but I verbally, I said it pretty close to right anyway. And down here you see alpha plus the beta plus lambda. I wrote it out, and that's what I got to at the end there. So I definitely have 1, 2, 3, and 4 done. Now let's go to number 5. Show that for every alpha in C, there exists a unique beta in C, such that alpha plus beta equals 0. So, you know that A plus negative A in real numbers is 0. And B plus negative B in real numbers is 0. So all I need to do here is make beta to be negative A, negative B. We'll prove uniqueness later. So direct proof, you add alpha plus beta together. And so you add the real parts and the imaginary parts. That gives you 0 plus 0. And that's defined as the 0 in complex numbers. So we found there, so you don't know if there's a unique one, but you know that we've shown that it does exist because we gave an example of one. Now for uniqueness, obviously I started to do something and it wasn't what I was happy with. So then, during my lunch I did, well, beta 1, let's say we have two different additive inverses, beta 1 and beta 2. So, alpha plus beta 1 equals 0, and alpha plus beta 2 equals 0. All right, I didn't write all that out, but, I thought it. So, beta 1 equals beta 1 plus 0. We already know when you add the 0 complex number, it gives you back the thing. That's like an axiom. Well, 0, if alpha plus beta 2 equals 0 also. So I can replace 0 by alpha plus beta 2. All right. Because we proved associativity, we can add in any order here. But beta 1 plus alpha is the same as alpha plus beta 1 by commutativity of addition, which we showed in exercise 1. And alpha plus beta 1 is 0. So we have 0 plus beta 2, which is beta 2. So we showed that beta 1 equals beta 2. So we used the fact that both beta 1 and beta 2 add to 0 in order to show this. So this shows that if you have two different beta 1s and beta 2s, they're actually equal to each other, which means, in other words, their real parts are equal and their imaginary parts, they're a unique complex number. So uniqueness was right over here. Okay. Number 6. Show that for every alpha in the complex numbers with alpha non-zero, there exists a unique beta in C such that alpha beta equals 1. So we showed the additive identity, so now we want to show the multiplicative identity. So, we had to find it. Now, I know that multiplying by the conjugate gives a real number. And I know that dividing by the same real number gives 1. So the idea is to do alpha conjugate over, what is it, like, over a squared plus b squared. So that's like the magnitude of alpha squared, isn't it? Because the magnitude of alpha is square root of a squared plus b squared. So if I square it, that'll give me a squared. So that's what, so alpha conjugate over absolute alpha squared is the inverse in, like, summary. So we just check it to show that it works. So down here, sorry about my scribble during lunch. To do all these problems on video takes time. So you have alpha beta So a plus bi is your original alpha. And beta is, yeah. So I did a minus bi over a squared plus b squared. I multiplied it out. If you multiply this out, you get a squared plus b squared. B, c, and ba and minus ba are 0. So the imaginary parts cancel. A times a is a squared. B times b is b squared. I times I is -1, but there's a subtraction. So the two negatives make a plus. Now we do the same method we did up here to show uniqueness with the 0. We're going to repeat the same method. So beta 1, and let's assume beta 1 and beta 2 are both multiplicative inverses. Then beta 1 is equal to beta 1 times 1. But 1 is alpha beta 2. Well, associativity of multiplication, which we showed in problem number 3, let's me multiply beta 1 times alpha first. And beta 1 times alpha, by the commutativity, which we showed in the section earlier on in the previous video, is the same as alpha beta 1, which is 1. And 1 times beta 2 is beta 2. So that shows beta 1 equals beta 2, even though I didn't write it all out. All right, I explained it to you. If you need to, you can just do the problem, listen to me, and write it out if you want to see it in detail. If you need me to write something out in detail, let me know, but there's no way I'm going to get through the majority of this book and do a lot of the problems. If I write every single detail out, it's going to take forever. So that's why I'm doing this sort of the fast way. I'm scribbling it out during lunch, and I'm explaining it to you unscripted. All right, show -1 plus 3i over 2 is a cube root of 1. That means we got to cube it. So you see here in parentheses, he says, meaning that its cube equals 1. I mean, he sort of gave you a hint to doing the problem. I'm just going to cube -1 plus root 3i over 2. I don't know if you hear my cat meowing in the background, but anyway, -1 plus root 3i over 2 times -1 plus root 3i over 2. So -1 times -1 is 1. Root 3 times root 3 is 3. But the I squared is -1. So you're doing 1 minus 3, which is where -2 comes from, for example. -1 root 3 and -1 root 3 is the -2 root 3. 2 times 2 is 4. So now I take what I got here, and I'm going to use this down here. So to do the cube, this is the square. Multiplying by another -1 plus root 3 over 2i is going to make the cubing of that. Multiply it by itself. Here's 1, here's 2, and this is the third one that I'm multiplying. So that's cubed. So what I'm doing is -1 plus root 3 over root 3i over 2 to the third power. That's what I'm doing to cube it. So we did that here. And, root 3 times root 3 is 3. 3 times the 2 is where I got the 6 from. Negative 2 times negative 1 is positive 2. Minus 2 root 3, minus 2 root 3. What is this? The minus and the minus here make a plus. The minus with the plus makes a plus. So that's where you get 2 root 3 minus 2 root 3 over here. That's why this is going to add to 0. So you have 6 plus 2 plus 0, 8 over 8. And 8 divided by 8 is 1. So it negative 1 plus root 3i over 2 is a cube root of unity, because when you cube it, it gives you 1. All right, so I talk fast there, but that actually means we've done problem numbers 1 through 7. So in the next video, I'll probably read some more in the section before going, because I don't remember us reading anything about square roots anyway. So but we were talking about the lists, and it does look like he's using lists here, so I don't know. I'll have to think about that. Anyway, thank you for listening.